Hello, YouTube. My name is Oscar Scholin, and today I will be discussing with you Euler's identity, which is e pi I plus 1 equals 0. Now, Richard Feynman, the famous physicist, described this equation as our jewel, as the most remarkable equation in all of mathematics. And I think he's absolutely right. It is something that is so incredibly beautiful and profound and elegant. And if you're religious, some people might cite this as sort of a proof for the existence of God, because it just so well exemplifies the well-structured nature of our universe. Because how else? I mean, something like this just doesn't seem like it should be true, but it is. And if you're a scientist, there's still this, or a mathematician, there's still this sense of awe at this equation. It's just because it's so remarkable, because we're combining the idea of E, Euler's number, pi, so circles, right? I, imaginary numbers, and as we'll see later, sine and cosine functions. So we're combining all of this in this very neat, very simple, very elegant expression. And so it's fascinating for me. And this is just an example of the true power of mathematics. You know, mathematics really is the language of the universe. And I believe that we can master that language in order to represent the natural, wondrous, enigmatic nature of our universe. But today, why don't we break down this very poetic equation? Why don't we break that down and kind of come to an understanding of why this is? And so let's first start off with a more conceptual idea of this identity. So let's look at the function e to the x, for example. Well, what's so special about this function? Well, it's because if we take its derivative, we end up with the same value. So in other words, e to the x is a unique function because it is both its derivative and its antiderivative. Right? If we take the integral, we get the same thing. So that's kind of an interesting idea. So, why don't we look at this in kind of a more physical sense? So let's say we have a position function. We'll call it x of t. Oops. X of t. And we have a velocity function, x prime of t. Right? So, okay, let's say our position function is e to the t. Our velocity, our derivative of e to the t, is just e to the t. So what this is saying is that e to the t is a function such that its position vector, if we are representing this as a vector, is equal to its velocity vector. Now that's a very interesting idea. Now let's say we have e to the 3t, some constant up there, right? Well, by the chain rule, the derivative is simply 3e to the 3t. So we have a velocity vector that is 3 times the length of our position vector. Okay, so, well, where am I going with this? Well, what happens when we throw an I? We throw an imaginary number in the exponent. What does that do? Well, our intuition might tell us it's going to be the same thing by the chain rule. But what does multiplying by I look like? What does that mean for our relationship between position and velocity? Well, I think we should draw a graph. So let's say this is the complex plane. Let's say this is the real part, this is the imaginary part. right? So what multiplying by I does is giving us this 90-degree rotation from our real axis to our imaginary axis. So in other words, if we have a position vector here, x, right? Position vector x, we need a velocity vector. We need our velocity vector to come off at a 90-degree angle. Okay, so we're rotating by 90 degrees. And we know if for this is to be true for all values of t, what this ends up looking like is a circle. Terrible circle, but pretend. Oh god, this is absolutely terrible. You know, drawing circles is hard. Let's just fix that. Let's try this again. Oops. Okay, so it's still a little wonky, but like pretend it's a circle. It's a circle. So the only way where we have a position vector, or we have a velocity vector that's coming off at a 90-degree angle to our position vector is in a circle. Try and fix this. The rest is okay, but this portion is bad. Yeah. Is in a circle of radius 1. And here's I. And so as we move around this circle, what we find is that if this is, so this is modeling e to the I t. What we find is that as we move around the circle of radius 1 at a speed of 1 unit per second, this function will give a value of a distance after we travel t radians. So let's say this is my position, and I travel pi radians. So I'm going. I've now traveled -1 real units, right? So I can say here that it's e to the I pi is -1. So let's see, so this works with our identity. E to the pi I plus 1 equals 0. If I've said e to the I pi is -1, -1 plus 1 is 0. So there we go. We have just proven Euler's identity in this very conceptual way. But now let's revisit this complex plane. But let's do it a little bit more of a mathematical way. Let's instead say we have a function z. Let's say z is modeling this complex plane. So let's say z is equal to x plus I y. The y-axis in this part is the imaginary axis, so we throw in the I. Well, let's try writing this in polar coordinates, where we know x is our cosine of phi, and we know y is our sine of phi. Okay. So if we just write this in, we would get z equals r times the cosine of phi plus I sine of phi. Okay. So now let's take the derivative of this function with respect to phi. What do we get? Well, it's r, the derivative of cosine is negative sine. And the derivative of sine is just cosine. Okay. Well, see if you notice something. This is simply I times our initial function z, right? If we just ignore the r's, we have cosine of phi plus I sine of phi. If we multiply by I, this gives us I cosine of phi. And we know I squared is negative 1, so minus sine of phi. So now, we have a differential equation that we can say. We can say that dz d phi equals I z. And if we multiply both sides by d phi, divide by z, we will get dz over z equals I phi. Or I d phi, yeah. Okay, so if we integrate this, we get the natural log of the absolute value of z equals I times phi. Okay, let's solve this equation. Raise both sides to the power of e. And we get z equals c, right, plus c. So we get c times e to the I phi. Okay. Now, let's look back at this function. If we set, so as we discussed earlier, we know that our circle has to be radius 1. So if we let r equal 1, and we plug in 0 for phi, we get z equals cosine of 0 is 1, sine of 0 is 0, so we just get rid of the I, so we get 1. So given that, I'm just going to write it here, z of 0, yeah, actually, because it's a little tight on space, I don't want to erase this. I'm just going to bring this up. So I'm gonna, since I know r must be equal to 1, and I know that z of 0 gives me 1, I can solve for c. So I know that 1 must equal c anything, and then e to the 0 if it's just 1. So therefore, c equals 1. So now I can say that z equals e to the I phi. And now, let's come back over here. Just erase this. What I can say is that I have e to the I alpha, or phi, I don't want to say alpha, e to the I phi is going to be equal to here. And we know that r has to be equal to 1. So it's the cosine of phi plus I sine phi. Okay, so we've now just proven this. And now let's just see if this satisfies the identity. If we are to plug in e to the I pi, we are to get, well, okay, cosine of pi is negative 1, and sine of phi, well, that's sine of pi, rather, is just 0. So we get e to the I pi equals negative 1. Again, that's what we got down here with our other conceptual method. So again, we have negative 1 being e to the I pi, plus 1 gives us 0. So we have proven Euler's identity. But this, we just introduced, is interesting because we are dealing now with cosine and sine functions. And as I drew here, we can think about it as relating e to the I phi, relating this to a unit circle, but on this complex plane dealing with both imaginary and real numbers of radius 1. And this is very important when it comes to higher level trigonometry and the other usages of this idea. But, so this is kind of cool. So we're now back with the circle, but now thinking of it almost like a unit circle, but in the complex plane. So that's pretty interesting, right? Okay, well, now I think introducing this idea of cosine and sine is important. And that's, yeah, it's going to be important for the next way and the final way that I will do today, proof of Euler's identity. So let's just erase this. This will be the calculus heavy, not necessarily heavy, but the calculus focus. Oops, I did not mean to erase that. There we go. Okay. So again, as we first started, we looked at the function e to the x, right? Let's return to that. How can we represent e to the x? Well, if we use the Maclaurin series to represent that, we will say it's the sum from n equals 0 to n equals infinity of x to the n over n factorial. Right? So let's start writing this out. This would be, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. The idea being we have x, raising x to the n over n factorial going from 0 to infinity, so that's why we have the dot dot dot. So going on forever. Okay. Well, but again, we have this I in our exponent. So if we come back here and we throw an I in there, what is this going to do? Well, we're going to have 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4th over 4 factorial, and I'll do a couple more just because it's important. So it's the same idea, the same sum, but now we're just throwing an I with our x. Okay. Well, now let's simplify this. So let's first just define some powers of I. Well, we know that I itself is just the square root of -1. It's a 1, right? So we can thus conclude I squared is -1. I cubed is -I, and thus I to the 4th is 1. So let's extend this. So 1 plus ix, that just stays the same, minus x squared over 2 factorial, minus x cubed, ix cubed over 3 factorial, plus x to the 4th over 4 factorial, and then it's just going to start repeating, so minus ix to the 5th over 5 factorial, and again going on. Okay, well, how about we factor some things out? Let's say, we can say this is 1, so minus x squared over 2 factorial plus x to the fourth over 4 factorial plus going on. Plus, now we'll deal with the I components. And we know the I components, we have just x, right, minus x cubed over 3 factorial. And then plus x to the 5th over 5 factorial. And then again plus dot dot dot. So you might be asking, okay, well, why go to this trouble? What has this gotten us? Well, if you have taken Calc 2, you might notice, again, more Maclaurin series popping up. This is merely the Maclaurin series for the cosine function. And this is merely the Maclaurin series for the sine function. So now this is really interesting because, again, we can say, if we go over here, we can say, again, e to the ix is going to equal cosine of x plus I sine of x. And again, as we showed earlier, you plug in a pi for x, you get -1. And again, that's what this is. Plugging in the -1 plus 1 gives us 0. So a completely different way of thinking about it. This is thinking about it in terms of Taylor and Maclaurin. Series. Taylor and Maclaurin series. Using that, again, the definition of e to the x, plugging in the I, factoring it out. So that's just another interesting way. And then, for me personally, I think this is the most fun way because it's sort of the most straightforward and it's just calculus. But as we saw, I mean, there's so many different ways to prove this identity. And there's so many different interpretations you can get of it. I mean, this is using this thing about in terms of series, representing these functions in terms of other functions, sums. Or you can think about it in terms of the complex plane and rotations, or you can think about it in terms of polar coordinates. So there's really and differential equations. So there's really so many different applications, so many different ways of interpreting Euler's identity, and that's what adds the extra depth. Not only is it such a beautiful equation, but there are myriad of ways to prove it and to think about it, and so it again is just fascinating for me because we are with one equation we are unifying these completely this seemingly disparate ideas, and we can use many different approaches to end up with the same result, which to me is just fascinating. And this is really the beauty and the power of mathematics, as I said earlier. Again, using mathematics really as the language of the universe, and it really is. And when this to me it's just poetry. It's the poetry of mathematics, and it's absolutely wonderful, and it's really fun. Yes, really fun to prove, fun to think about. It's awesome. And so in the next video, I'll be talking about the general Stokes theorem, which is my all-time favorite theorem. Just as beautiful as Euler's identity, and it has so many applications. It's just absolutely wonderful, and that will come out in a couple of days, maybe a week or so. But yeah, so if you have any questions or comments, please leave them below, and I'd be happy to answer them and have some awesome discussions. And if you have any suggestions of other videos to make that'd be awesome. So I'm planning on doing a video on the General-Stokes theorem. Also, we will do a video on Feynman integration, which is a really cool integration technique in higher level calculus that I think, it's just incredibly fascinating and just also quite fun. But yeah, so I hope you have a great day, and remember, stay curious and have a mathtastic day.